Welcome, everybody. Thank you for coming. I'd like to introduce Dr. Arinbjörn Kolbeinsson, who's going to speak to us today. He is currently serving as a visiting scholar at the University of Virginia, focusing on responsible and accurate models for health and biomedicine. His recent research explores the editing and efficiency of language models, along with the development of composable interventions techniques. And previously, he was a machine learning scientist at Evidation Health Inc., where he developed innovative methods to predict health outcomes using high-frequency multimodal data. I'll let you take it away.
Thank you. Thank you for the introduction. Let me just share my screen. There's someone else sharing. I think I can cancel that. And you will let me know if you see the intro slide. It should be there.
We can see it.
Okay, perfect. Yes, thank you. Thank you for the introduction. Yes, I'm Arinbjörn. Great, thank you for inviting me. It's great to be here and be here. I mean, coming from Virginia, but actually coming from Switzerland because I have a remote visiting position with the University of Virginia in Tom Hartrigson's group at UVA. And I've been doing some very interesting work there with a huge team of collaborators that I'm very excited to tell you about. So let's begin by just saying that this was a very large group that came together to put all of this, to put a huge amount of work into this. And I couldn't even fit all the affiliations into this. So you have to look at the paper to see the entire list of affiliations. But it was a big effort, lots of ideas and some very interesting results that I'm excited to share with you today. So the problem that we're looking at is can be drilled down into three factors. The first is that LLMs are very expensive to train, and here I'm talking about pre-training. This can, be on the order of millions of dollars for larger models. And another factor is that post-hoc interventions open up capabilities. And what I mean by here is we can take a pre-trained model and we can fine-tune it to adapt it to a new task. We can compress it to better adapt it to smaller devices, or we might want to debias it to remove some harmful content that it might be generating, or we might want to unlearn something. Perhaps during the training set there was accidentally someone's phone number or bank account details somewhere in the training set, and we want to remove that, but we don't want to start from scratch with another set of $5 million to train a new model from scratch. And those are all very interesting research avenues, but up until now they've all been looked at almost entirely in silos. So the compression research has been focused on compression, debiasing is doing debiasing, even knowledge editing, sort of adding in new facts to a model is still quite succinct from unlearning, forgetting making the model forget the fact that was accidentally in there. And we don't know how all of these interact together. And this can be a problem because you might very well like to both compress your model to fit it onto a mobile device while also want to debias it or add in some new, do some new knowledge editing onto that. So what we do is what we study here is actually how do these compose? How do these post-hoc interventions compose? And what we did is we set it up by looking at three different classes of post-hoc interventions. So the first one is knowledge editing. So this is updating a new fact. So many of the older models are trained from a time when the most recent Olympics were in Tokyo, but you want to update that now to say the most recent ones were in Paris. there are ways you can do that. So and then there are many ways to do knowledge editing. You can fine tune the model. You can do LoRa. You can do Memit, which is a specialized knowledge editor. You can even do in context knowledge editing, so where this sort of or you might adapt that with a RAG type model. And so the three that we look at are fine tuning, LoRa, and Memit. And for compression, which is the second class of interventions we look at two subclasses. One is pruning, model pruning or sparsifying, where you're essentially setting a few weights to zero, and two types of model quantization, where you can go from, you're usually trained in 16-bit, and you can take these down to 8 or 2 bits with different levels, and most of these are mixed precision as well. And then we look at three types of unlearning methods: gradient descent, gradient difference, and RMU. And what we do is we want to study how all of these compose together. How do you, for example, if you want to compress a model and also unlearn something that was in the pre-trained model, what happens to the compression when you do unlearning, and what happens to the unlearning when you do compression after you've unlearned something? So while studying this, when we started, we realized that we had to come up with a framework for studying this in a consistent and standardized way. So we developed two new metrics for this, which we call order-free error, which is the error of the interventions, irrespective of what order you do them in. It should be self-explanatory from the name. So it's if you do maybe do first compression and then do unlearning, what's the error? And then you do unlearning and then compression, and then you take whichever gets the lower error, that's your order-free error for that composition. So the entire framework is based on these compositions. In this study, we look at pairs. So we have a pair of compression and unlearning, compression and knowledge editing, and we look at the order-free error. So irrespective of the order, what's the lowest error we can get with that composition? And then we also look at order sensitivity, which looks at that intra-level order difference. So if you do compression first and then unlearning, and unlearning versus then compression, what's the difference? So does the difference actually matter? So for a model that you can, the order is completely invariant, they will get an order sensitivity of 0. If you had get no error for the first order and then you completely destroy the model for the second one, you would get perfect sort of 100% order sensitivity. And then we formulated these as well, but I do like graphical illustrations. So, and I'm sure many other people do too. So just don't spend too much time thinking about all the symbols. The really thing that only matters here are the two lines and the two shaded regions. So here we're looking at a type of intervention. Let's say on the x-axis, we can plot the sparsity level. So this is sort of the amount of compression. And we're going from 0 compression, so an uncompressed model, to complete compression. And then on the y-axis, we can plot the edit success. So how successful was our knowledge edit? So we're updating. Let's go back to our previous case. We're looking at updating the most recent Olympics from Tokyo to Paris. We do our method. Was our method successful? Yes, 95%. And then we can look at the level of let's just take 20% as our reference compression level. So if we do 20% compression first, and then we do a knowledge editing, we might get 75% accuracy. But if we do knowledge editing first and then compression, we might get 90%. And then this difference here will be defined as the order sensitivity. And then whichever is the higher, as the the lower amount of error, that is our order-free error. And then we can scroll through the entire sparsity range and get the order-free error area, which is this red shaded region, which would correspond to this, the integral there on top. And then the difference between the two is the order sensitivity. So in a perfect world, if two methods are perfectly composable, then these two would match up perfectly. Then it doesn't matter what order you do your interventions in, you'll always get the same level of performance on some defined metrics. And then that really becomes key, is what metrics do you use to define these compositions? So for our framework, we picked out a set of metrics, 3 metrics for knowledge editing, 2 for compression, and 1 for unlearning. And I'm not sure how familiar everyone is with knowledge editing, but you can imagine if you are just going back to the same example, you are updating the location of the most recent Olympics, and you can very easily check for edit success. So this is how successful were we in updating. If we ask you the question, where were the most recent Olympics? Is it going to say Paris? We can check for that. And then we can also check for generalization. So we can slightly rephrase our prompt and say, where was the most recent large athletics gathering held every 4 years held? And if we should rephrase it like that, it should still say Paris. So that's our localization, our generalization metric. And then we have our localization metric. So we do not want it to mess up anything unrelated to this question. So if we ask, what's the capital of Japan, we still wanted to say Tokyo. We don't want it to update that to Paris. So we have these 3 knowledge editing metrics that we use. And then from compression, we measured general model utility as the performance on MMLU, a pretty standard metric. And then it's I don't know if anyone's familiar, it's a set of a questionnaire that's often used in language models with general questions and some just separated into subcategories as well. And for unlearning, we use the weapons of mass destruction proxy dataset. So here, the task is to unlearn a set of facts about certain weapons of mass destructions, bioweapons, nuclear weapons, and then there's a questionnaire at the end. So your goal is to take a pre-trained model. We can measure how much it knows about weapons of mass destruction. Then we apply a given unlearning method, and then we check if it actually unlearned those facts about the weapons of mass destruction that we're looking at. So we take all of these together, and we have our, was it in there? Did I put it? Yes. Okay, I put the Llama 3 there. I can talk about it here. So all of these are ran on the Llama 3 8 billion. So all the results that I'm going to go through are on that model. We are also expanding this to Phi 3 Mini, the Mistral 7 billion, and Llama 3 70 billion, just to see if these results hold across different model families and parameter scales. So what we do is we do every combination of these, and it turns out that we end up with over 300 different Llama 3 models that we've intervened in different combinations. And then we look at, what do we get? So I'm going to take you through our 6 key findings one by one. So the first one, or actually before I do that, let me stop here and just ask if there are any questions at this point about the setup before we go into the results. Okay, I guess that's clear. But yes, please feel free to stop me at any point if something's not clear. So our first key finding that we see is that model compression degrades editing performance. This is not the most surprising finding. This is something that we did expect to see, but what we were really curious about is what is the shape of the performance degradation and what are the different effects that we see depending on what model, what editor is being used. So we see that this is true, the model compression degrades editing performance across the board. But we also do see that, yes, let me just explain just the first figure here. So this is like we said, so on the bottom, we have the sparsity percentage. So at 0, where we have an uncompressed model, just the regular Llama 3 model that has only been edited with these 3 different editors. And then at 25, we have 25% compression, and the full circles, that means that we did editing first, followed by compression. So we see that, for example, fine-tuning, the one on the left, that it's a fairly good baseline, given that Mehmet and Laura are more specialized versions of they're not exactly fine-tuning, but fine-tuning gives a good baseline, and it's a surprisingly strong baseline, particularly if you compress a model first and then fine-tune it. Whereas if you fine-tune a model first and then compress it after the fact, you'll get as much lower ranking here. And then the green and the red, the orange and the green are the 2 different methods, or Wanda and sparse GPT, 2 different pruning methods that we were looking at. How does it really matter which type of pruning method you use? Do they have different properties? And when they compose with different ones, and we see that Wanda is particularly strong when composed with fine-tuning, the green marker, whereas on Laura, we see sparse GPT is a bit better. So this was our one of our key findings, and we also see that whereas Mehmet starts off lower in the edX success, it maintains a pretty strong score into the higher compression regimes. So it can compare to, let's say, fine-tuning, especially in generalization. So where you're changing the phrasing of the prompt and seeing if it still remembers this new fact that you've injected into it. Mehmet maintains that quite well, even at 45% pruning, whereas Laura starts off very well, particularly in edit success. It's not so good in generalization, and then we just have a linear decline almost through that. Yes, is there a question? No, okay. And then we have another message with the strict locality, and then our MMLU, which is our general metric, which I'll come on to a bit later on. Our second key finding is that editing performance depends heavily on the order of the interactions. This could also be seen in the previous slide, but I will also show you here just a quick demonstration that we did. This actually didn't make it into the paper, but I wanted to include in the talk because I think it's kind of cool, but it's not as polished as the rest of the things. So we were looking here at so here we're changing where are the next Olympics going to be with an old model where Tokyo was actually the next. It was trained on a data that was heavily biased towards Tokyo being the next Olympics. So these are the logits of the model after pre-training. So the ones that we start off with. And we see that Paris, which is our target, was actually in third place when it came to that. So then we tried doing our editing and then compression just to see how the logic would be affected by that. And we see that after editing here, we can very successfully get Paris to be the output that we want after that target. And then we see after compression, the whole landscape of the logic changes quite dramatically, like we would expect. And Paris here remains as the second highest after an empty space, which took over for some reason. And then we, at the same time, or in a different model, we looked at the other way, doing it the other way around, first compressing and then editing. So we first compress it, we again see a different landscape, but Tokyo remains the highest one. So in this case, compressing it, it does not lose its output, its pre-compression output. It still keeps that as Tokyo. Whereas if we now try to edit this compressed model, and this is a sparsified model, we cannot get Paris to become the top logit. So this was an unsuccessful edit here on this compressed model. And although we didn't actually, this is also on Llama 2, an older result, but we saw that these interventions, the order that they have in, have a huge impact on the models, and in particular here the logits, the output logits of the model, and the scale and the relative magnitudes of them, depending on which order you put them in. So another key finding is if we look at different categories. So we've been looking now just at pruning, but we can also bring quantization into the play. So if we again look at knowledge editing, but now on a quantized model, and not a pruned model, we see that editing and quantization go together much better. The axes are now also increasing, but we of course start with 16-bit, so that's the unquantized model, and then we quantize them into fewer bits, and we see that even at 3 bits, 4 bits and 3 bits, we're getting very strong performance across the board with AWQ. AWQ seems to be a very strong quantization method, and it plays very nicely with other methods as well. So it's not degrading their performance as much as GPTQ and the pruning models. And what's also interesting here is we see that there seems to be some regularization effect here when working with Mehmet. Even quantizing it down to 8-bit, we get a slightly higher score. So we hypothesize that this might be a regularization effect, and there has been previous work showing that regularization can be improved with quantization. The quantization can act as a regularizer, potentially similar how some of these constraining methods help reduce overfitting. So we don't know if that's the case, but it was an interesting finding that we saw there. Our next finding is that utility evaluations, overall utility evaluations, are not great markers for composability, and this can be a dangerous pitfall if you're prone to using just MMLU for your model performance evaluations. So we saw here, so this is looking at edit success again, and with different compression methods. And we can see that if we look at MMLU, which is on the right side, I'll just highlight here, we see that AWQ and GPTQ get the same MMLU score. So, and this is MMLU error, so it's 1 minus to get the MMLU score, so it's around 60%. And from that, you would infer, okay, AWQ and GPTQ didn't really impact my model that much. They're both getting the same MMLU scores. But if you actually look at the edit success, you can see that GPTQ has degraded the edit success quite significantly, and the error rate is now 21% when you're checking if the edits are actually successful. Whereas AWQ, exact same MMU score, but it's actually retaining the edits that you input into the model. So this tells us that we really need to be careful in the evaluations that we use. And if we're looking at edits, when you do edits, that's a different class of knowledge in the model compared to the knowledge from the pre-training set. And if you do another intervention, that new knowledge in the model, that new data, that one is going to behave differently to the rest of the older data that was trained on. And this is very particularly of relevance for deployment cases. So our next key finding was that compression also hinders unlearning, and quite significantly so. But overall, RMU performs the best. So these can be quite confusing, these plots in some ways, but overall the key takeaway here is that compression and unlearning do not go together very well at all. And although having said that, RMU does perform better than the other methods, particularly when looking at W. So the dashed line here that we have, that is the baseline that we want to compare ourselves. That means it's getting a random guess on the WMTP dataset. But here, it's also this was also a tricky setting, because what happens when you compress a model too much, like we saw in the sort of the previous case. I'll just go back to here. If you just look at the bottom row, is that if we look at just general performance of the model, if you compress a model too much, you will destroy it. You will just get random outputs. It will just give you random tokens. And on a setting like unlearning, where we're testing against the WMTP dataset, if you've unlearned it, a destroyed model has also unlearned whatever you were trying to unlearn. So it's a hack. You can just compress it, destroy the model, and bam, you've unlearned all the toxic materials that you were trying to unlearn. So there's this sort of sweet spot of having unlearned it, still maintaining a good MMLU performance while having a low WMTP performance. So finding here is the sweet spot is the key factor. And our final finding is that while both were while unlearning was very uncomposable with compression, they can be highly composable with knowledge editing. And in particular, RMU performs very well across the board. And our hypothesis there was this might be due to the way that RMU works by targeting specific layers and also working in specific dimensions, constrained dimensions in the parameter updates that it does. And it might be sort of working orthogonally to the knowledge editing methods that might be editing completely different sets of parameters and not interfering as much, whereas compression works very differently and is much more prone to conflicting and editing and updating parameters, which either have been edited or unlearned. which can be very sensitive. So any small changes to those targeted interventions by compression can have huge and can have a huge impact on the effectiveness of the sort of these targeted interventions. But we see that with RMU, we get really great scores, and also with LoRa, we get, which again, in this case, we've constrained it to, it's a 32 layer model. We apply LoRa to just 5 of the layers, and also it's also a low rank method, so it might be working orthogonally in certain ways. So what are the key points that are the most important from this? So that is really that model compression harms other interventions, and it has a very significant effect, and it also happens way before model compression starts to harm general model utility significantly. So like we saw before, we can compress a model with GPTQ and we get the exact same score as we would with AWQ, another quantization method, the same MMLU score, but the edit intervention is significantly harmed. So this means that practitioners who are trying to do those multiple interventions have to be really careful with which method they use. So AWQ and GPTQ are different, they work differently, and depending also on what knowledge editor you're using, they will have different effects on your overall score. So what we're working on now, which is a future work coming from that, first one is creating these recipes for which sort of ingredients. How do you gather how do you pick a knowledge editor with a certain quantization method? And you might be limited. So let's say your model only supports AWQ, and then you might want to pick a specific knowledge editor based on that. Or you have to work with LoRa or fine tuning because you're limited memory, and then you might want to pick a specific unlearning method because of that. So that's something we're working on, is creating these recipes for which methods exactly go well together, so that people can, and researchers can, and also practitioners can take start off from a good starting point, knowing what's going to happen when they put all these ingredients together in the same bowl. And we also see that unlearning compressed models is particularly difficult. And this might be a very interesting research avenue, particularly now with more language models being deployed on device. We've seen that now with the new iOS 18 update. Google is working on their on-device options. And if you compress a model, most of these methods are compressed in some way before they're deployed on a smaller device. And then if you do that, and then you realize, hey, there's something not so good in that model that we just deployed that over across 1 million devices, we need to do some unlearning, and each one might be sort of personalized. So you can't just wipe them all and start from scratch. You have to unlearn it. That might be difficult if you don't use the correct unlearning method. And right now, the unlearning methods that we're seeing are not particularly composable with any of the compression methods. So that's an interesting research avenue, or might require some new ways of deploying those models. And finally, the order of the interventions is very important and changes the metrics, both module utility and also the intervention specific metrics quite substantially. So this is also very important for practitioners to know. You have your ingredients in your bowl. In what order do you add them in? So, and this also particularly for larger models, you might not even have the, even though you can do post-hoc interventions and they're much cheaper than training from scratch, many practitioners who are not at the large industry or large academic labs can do multiple interventions and do the hyperparameter search themselves. So we want to be able to give them directions on what's the best starting point for applying a certain set of interventions that you want to do, what order should you do them in, how important is the order, and where do you start. So that's our key things, and we're really interested in sort of exploring each one of these in detail and also taking the entire the framework forward, which is by looking at where, because there are many research avenues here. One that we're exploring is sort of a unified intervention method. So can we create a method that both compresses and edits a model at the same time? So, or a compression aware method, so that you can tell a compression method, hey, I've edited the model, these parameters have changed, so be extra careful with those parameters. And but that's ongoing research work. So I just want to thank you all for listening. I'm really curious to hear everyone's thoughts and any questions or thoughts that you might have. Thank you.
Great talk. Thank you so much for taking the time to speak with us. We'll open it up to questions. If anyone has any questions, feel free to type it in chat or unmute yourself. Looks like we have the first question in the Q&A chat. They say, thanks for the talk. They were curious, did the generalization affect, I was curious whether generalization is affected when compressing the models.
So yes, let's go back to this one here. So yes, so generalization. So this is when so this is edit generalization. So how does the prompt, changing the phrasing of the prompt change when you compress the model? So we do see that is affected by the models, by compression, but we also see that it's the behavior of degradation to generalization and edit success is very different depending on what knowledge editor was used, and also in what order it was deployed in, particularly for fine-tuning. And we'll see, yeah, that Mehmet maintains pretty good generalization even at higher compressions, whereas fine-tuning degrades quite quickly after the sort of 30%. And Laura is quite bad at generalization across the board, but does not have this collapse that fine-tuning and Mehmet have. It's just a linear degradation of generalization. Does that answer the question?
They say it does. Great.
Okay.
Yeah, thanks for answering that. So another question, so you mentioned toward the end, talking about the kind of issues that a company like Apple might have, where because they're deploying these to millions of devices, if they need to make a change later, that can be hard when they're different models. Do you have any suggestions, like if you were like an engineer at Apple, how would you approach kind of dealing with these kind of issues?
Yeah, that's a really good point. I think it's about, I think they really have their work cut out for them. Because they really have to think many steps forward, particularly if the model, I don't know the details of the models that they're deploying, but if they are going to be fine-tuning any of the models on device and adapting it to certain user characteristics, and then deploying some of these methods after that, they could very well run into problems. And if they don't do it right, they could get themselves into a corner where they either end up with a bad model or they just have to start from scratch or do some sort of student trainer to transfer something to another model, but that would be very expensive as well. So I think what we really do need is a better understanding of how these models are interacting. And we think that this gives a very good foundation for that. But also what we need are methods that are aware of the other interventions that might happen to a model. So compressing a model, like I mentioned, compressing a model, knowing that there are certain parameters that are different. Not all the parameters are the same. And the same for unlearning. If you unlearn something, you might have some very sensitive configurations related to those outputs, and you don't want to mess with those when you compress, because although we haven't seen that that's happening, but you might end up with a position where you unlearn something in your pre-trained model that was really bad, and then you compress it, and then the fact reappears after compression because the unlearning was so sensitive.
That makes sense. Thank you for the very detailed answer. We have another question. What are the main practical concerns, know-hows, challenges, etc., when you design target metrics for evaluating LLM's intended success?
So wait, I'm gonna look at the question again. Main problem when you design target metrics for, so I guess this would sort of be, are you asking about these like these knowledge editing in particular, or just any of these intended success sort of MMLU, WMDP? So what we used is we've used these because most of these have been worked in sort of silo and isolations. We picked the metrics that were being used in each sort of sub-research community. So whether that was knowledge editing, compression, and learning, we picked sort of what are the metrics that matter to the researchers doing knowledge editing methods and unlearning methods. And sort of based it off on that. But what might actually, because what we're seeing is that they don't work really well together. And this isn't sort of what we try to do here with these is sort of create a unified metric that is independent of the intervention target, but still sort of based on that. So if you're doing editing, you look at edit success, but then you get this sort of these errors, the minimum composed error and the order invariance that should tell you if these methods are, the motivation was to see if they were very composable. I don't think that answers your question perfectly, but I think if that's what you mean by the target metrics.
Yeah, we'll let them follow up if they have any
Yes.
further clarifications. We have another question. How do you think QLoRa's performance in terms of trends in compression and editing would be? Will it be
Yeah,
similar to LoRa?
yeah, this is a really good question that we're really interested to explore further, because you have that combination. It is a combination of quantization and sort of fine-tuning or that can be used for knowledge editing, and seeing how that, whether we see these getting better across the board. So I think what we saw was that LoRa was already a very good baseline to begin with. Not so much for edit generalization, but it was consistently getting the highest edit success, but it was also very prone to degradation at higher compression levels. So my guess would be that it performs better with the QLoRa performs better, but by how much, I would be very interested to see.
Thank you. That's all the questions. Oh, that's all the questions for now. Any last minute questions? Feel free to unmute or ask in chat. We'll give it like another minute.
Actually, one question not related to the talk. I think at the beginning you mentioned that you were working on medical domains for these LLMs. Can you talk a little bit about that? I know it's not the purpose of the talk,
Yes,
but
no, that's a good question. So yes, both Tom, the PI in the lab I'm at, and I, we both have worked on, and we actually started this sort of visiting scientist position that I have as in the health domain. But then we ran into these sort of interventions that we were looking at for health models in particular, and we saw that this was a fundamental problem in language models, but actually this can be very easily extended to computer vision and other domains as well. There's nothing inherently natural language processing about this, but that's what we tested on. But we are curious about building methods that help in the health domain and in this sort of updating facts. That's one thing, making sure that you have the best knowledge possible. So updating facts is important, unlearning incorrect information or sensitive information, and compressing models if you want to deploy this privately to devices, to users or individuals who want to have run these models themselves, are all very important. And if you want to do that in the health domain, you need some combination of these methods, but they're not sort of comparable at the moment before we did this work. So that was the sort of motivation. That was sort of what started us on this journey in many ways.
That's interesting. So you'll be doing experiments on medical domains, like for sanitizing or removing personal information, things like that. Is that kind of the next step?
Yes, that is definitely one of the many next steps that we're looking at, because we want these methods that we can use in the health domain, and we think this gives us a good platform for working on and building and researching these new models and new interventions.
Yeah, okay, thank you.
We have another
I see
question in
another.
the Q&A.
Yes.
Can you comment if the model size has any effect on your evaluations?
So yes, so those are preliminary because they're all still running for all the other models, but we see that with 5.3, which is the first one that we've sort of gotten quite comprehensive results on, that the general trends are the same. So the key points that that we saw on the 8 billion model. When we go down to 3.8 billion, I believe, the general trends are the same, but we do see some individual intervention differences. So it's more sensitive to the interventions, and the drop-off happens a bit sooner in many of the cases, particularly with compression. It's more sensitive to compression we see, but we also, what might not be, what is a sort of a confounder here, is that the Phi-3 model has not been released in the pure pre-trained form. Microsoft only released the instruction tuned version. And we believe that the instruction tuning is affecting the knowledge editing experiments. So we're seeing like MEMIT does not perform really well on the Phi-3 model, and we think it's because it's instruction tuned. We don't know. Or maybe the MEMIT retraining prompts have to be sort of tuned a little bit differently. We're using the instruction format, the template for 453, but we're seeing some interesting results there that we think might be due to the instruction tuning rather than the model size, but the general trends hold overall.
That makes sense. Well, I'll open it up for final call. If anyone has any questions, feel free to unmute or ask in chat. Okay, why don't we end it there? Thank you again